Hello, I'm Karlo. I'd like to introduce to you my research. Let's start with these two words in the title. The main field is thermodynamics, but we spice it with geometry. Let's visit the old Cartesian plane. With 2 points, we usually talk of the distance between them. The notion of distance and angle gives the Cartesian plane a certain kind of geometry. In thermodynamics, we also like to plot things. Points here correspond to thermodynamic states, but do we have a notion of distance here? The metric is the mathematical object that assigns a measure of distance between 2 points. In flat 2D, we have the Euclidean metric, or the Pythagorean theorem. Here in our study, we use the Ruppeiner metric. Here are some of its important applications. So, how do we actually play with the Ruppeiner metric? Well, first, we find the Ruppeiner metric of different model systems, and then calculate its geodesics and curvature. A geodesic is the shortest path between 2 points. Now we're ready to go over our main results. First, we divided the van der Waals state space into its different phases using geodesics. Using a slightly different formulation of the metric, we reworked a previous partitioning of the van der Waals state space so that it becomes more physical. In order to find general truths about the metric, we constructed our own general expansion of equations of state about a critical point. We plugged this general equation of state to the Ruppeiner metric and then calculated their curvature. The curvature generates its own phase boundary in Widom line. The Widom line, by the way, is the locus of isobaric heat capacity maxima. We then compare this alternative construction to the standard one. For the phase boundary, we see good agreement between the two different constructions, and we have provided a proof that guarantees disagreement. However, the same is not true in general for the Widom line. But for the van der Waals case, the agreement is exact, but only if we tweak a little how the Ruppeiner metric is usually used.